work that we did with him before and with Sanshi like in the past year. Okay, so we go over some introduction where I want to look at bound waveforms from the PM approach. And then I will try to describe one approach, which is trying to consider the beta subbeta recursion and what kind of it tells us about bound states from the amplitude resummation, and we'll see. And this will add to the amplitude action relation, and then we'll talk about boundary to bound, first in the conservative sector, and then I will talk about the relative sector, so extending the beta subbeta relative case, and understanding how to write waveforms, and match also analytic continuation with the PM results like that were already available. And then I will start also the fluxes at the end, if I have time. So I think that the discovery of gravitational waves really calls for new theoretical techniques to understand the two-body problem. And we should try to all kind of work together all these three phases of the problem, like the spiral, the merger, and the rig down. But I'm just going to talk about the spiral for the reason that I can apply perturbation theory, which is very close to amplitudes and the theme of this workshop. And we have in mind that at some point we'll put together in some ERB or Saltos framework to combine analytical and also numerical, I would say, techniques. Numerical techniques are also very important. So as I said, today we focus on the spiral phase. We look at some long-range contributions and where we can think about these objects, complex objects, as point particles with some interactions and finite size sets or spin. They can all be taken into account like in a kind of FFT framework. And this is a kind of nice reference of the work of effective field theory for extended bodies. I will back on stage. So why amplitudes? So there are some people in GRs. I want to give a motivation for this. So amplitudes are kind of gauging variant way of putting together like perturbation theory essentially, and they give you a new perspective, I think, on GR. One of these has been realizing how, for example, you can rederive Schwarzschild black hole from essentially amplitudes, like from point particles. So just consider point particle coupled to gravitons. You can reconstruct the Schwarzschild metric. And these, I think, give a really new, different way of looking at the problem. Like, so that's something very nice for me. And one of the questions we're trying to address is how can we study classical bound state with amplitudes? So I like this quote from Weinberg. We've seen my talk before, if you remember. So it must be said that the theory relativity effects relative correction bound state is not entirely in a satisfactory shape. So this is volume 1 of Weinberg, which is the usual standard textbook for quantum field theory. So I think there is still a lot to do about bound states in quantum field theory, and I will try to give a new perspective on this, hopefully. So we'll start with something very simple. So linearized Schwarzschild background. So this is the first approximation of the PM dynamics at 1 PM. And this, you can think about this as just solving essentially the background equation. So you have this potential linearized Schwarzschild, and this can be mapped completely in a solvable Coulomb problem. So you can completely map this. And the Coulomb problem can be solved both for scattering and bound, right? So you consider your Hamiltonian for Coulomb problem, you just consider the eigenvalue, and I just solve it with the standard quantum mechanics techniques. So if I solve it above the threshold with scattering plane waves, I find amplitudes, okay? Objects you are familiar with some continuous spectrum, okay? But I can also solve it below threshold and just find some normalizable wave functions, like something that looks like a Laguerre polynomial, right? In the quantum mechanics sense. And so this will update discrete spectrum. So we introduce also some notation for scattering and bound, which I find convenient. So you see here the potential depends on the coupling, or you can solve this problem analytically. So what happens? Is there a relation between scattering and bound wave function? We start with the 1 PM dynamics, just since we can solve it for bound directly. And the answer is yes. So if you look at the standard conflict per geometric function, the scattering on Coulomb, and you look at the bound analog of this in partial waves, you see that the scattering one is a sum of partial waves, right? So the scattering solution is a sum of partial waves, and it's every partial wave is labeled by quantum numbers, whereas the bound solution is directly labeled quantum numbers. So any meaningful comparison in the partial wave basis. This partial wave basis will become the input parameter space later. So this is just preliminary to that. And there is something interesting. There is a single branch curve prescription. So in general, if you need to continue in the energy, you might have two branch count prescription for this square root, okay? But only one seems to work. The reason is, roughly speaking, here you see there is a I p dot x, and here there is a minus e x. So to map this to this, you need a single branch count prescription. This is a kind of square root I was talking about before. So you can rephrase this in terms of this nice variable p tilde, p and p tilde, which are also used in some kind of WKB context, if you're familiar. And you can write this in this nice form. So you have one branch cut, analytic continuation, this p infinity. There is still this residue thing. So what happens? So there is a gamma function here. And essentially, this arises from the resummation, as we'll see, some the Born iterations. And you have to take care of that. So you have to take the residue over that gamma function to make a connection between the scattering solution in the partial wave basis and the bound one. So, and essentially, the residue comes from the bound state poles. But you see there is a direct relation between the two. So there is some hope that we can do some boundary to bound in general. But this is just a simple example. So we'll now go deeper. And one thing is that this can be considered some kind of scalar wave on a background in some sense. It's the variation of the wave function for a background. So it's a prototype of something that would be a waveform for the two body in some sense, if you consider a Compton amplitude, for example. So you can discuss this in perturbation theory. V depends on the coupling, so you can just look at the coupling. The point is the bound state energy pool is regenerated by iteration in a kind of Lippmann-Swinger approach, or Basel-Peters will see, like you can generate the pole by recursion. Essentially, the poles are generated by recursion. So if you look at this, you might simplify the map. Here there's a potential, and in some sense, only one potential, only one term is relevant, right? And this is, yeah, what I'm after, but we'll see how it arises. If this potential is generated by another particle, then we get the ladder approximation we're all familiar with in non-relativistic physics. But of course, we're interested in relativistic physics, and the generation of this is what is called Basel-Peter equation, which is just the amplitude recursion relation, essentially. And it just comes from Swinger-Dyson equation using LZ reduction of the 4-point Green function recursion relation. So you take this equation, and it was interesting enough, it was found by one particle physicist and one astrophysicist. So it's kind of a nice way to talk about gravity using this equation that's invented by those two big guys in the past century. And the interesting thing is that the 4-point function generated by an iteration of two massive particle reducible kernels. So the 3-level here that I was talking about is just iterated, and that's if you cut in the middle, an S-channel cuts, you see that this one generates the full iteration. So this is kind of generalization of this for the two-body problem. How can we take classical limit? And so that's what we worked out in the paper with Tim. So essentially, you just consider a classical two-bar expansion. I'm not going to go into details. We use this heavy particle effective theory. It's very convenient to keep track also of spin in general. And we want essentially exchanges to be soft, long wavelength, long range. What happens is that from the previous iteration, you see, previous iteration includes this two-body propagator, which is, oh, sorry. The two-body propagator, which is here in the middle. So what happens when you symmetrize over internal exchanges is that you pick up some refinement of this recursion relation, where the two-body propagator is replaced by the emotional recursion. Using this classical expansion, you just get delta function, which is the usual one in the wordline approach that directly there. And then you see this recursion in terms of the M kind of two-particle reducible pieces of the diagram. So you just iterate the ladder essentially one by one, but now in the classical sense, in the classical iteration. So there will be cuts in place of where there was the two-body propagator before. So now, and you can see it here explicitly. So this is just essentially like the Kona resummation. And indeed, like if you now go to hyperparameter space, you can just solve this recursion directly. And this recursion is solved in terms of an exponential, okay? And the interesting part is, of course, if you Fourier transform back, the gamma function that I was showing you before, the gamma function of Schwarzschild is just generated by this Fourier transform. So it's clear that if I look at exponents I'm going to have better control of the analytic continuation. And indeed, if most of you have worked on the boundary to bound, know that the analytic continuation at the level of the radial action, something that comes at the exponent of amplitude in the Applin-Large relation. There is a heterogeneization of spinning particles, but it's in the paper, but it's more complicated. I will talk a bit about spin, but not on how to derive this with spin. This is an example of the 2PM kernel conservative. So whoever has done some PM calculation here knows how to do this. So this is the three-level exchange, and there's the one loop diagrams, and you just get essentially the triangle contribution and the three-level. This is just to show something in the conservative dynamics of two spinless particles, that these variables over here are just function of conserved quantities. So the bending energy and the angular momentum. That's because you are on a plane, essentially conservative dynamics stay in a plane up to 2 p.m. Okay, if there is spin or radiation, that kicks out the plane, as we'll see. But in general, here you stay on the plane, so you can really talk about conserved charge. And these conserved charges are well defined also for bounds in general. Whereas like here, for example, the rapidity, you see a square root, of course, is defined for y greater than 1 in the scattering regime. So you have to do some analytic continuation, but these are kind of nice variables. Also, y is a nice variable, as we'll see, but just for a moment, bear with me with these variables. So, okay, this is the picture that was in the first paper on the boundary to bound by Kalin and Porto. So for this bending energy greater than 0, you have scattering orbits, while for bit being less than 0, you have bound orbits. And what they found was a way to relate, to do the negotiation of the radial action. And the interesting thing is that this kernel that I showed before can be written at least up to certain, or definitely up to 2 p.m. also at 3 p.m. order, like in terms of some, the conservative part, in terms of some radial action up to constant. This is the amplitude relation that's shown in the paper by Z and then revisited by these people. And this makes a connection with something that is known for classical dynamics, where we can better discuss the analytic continuation in terms of boundary conditions. So, you know, classical physics is nice because you have differential equations. And the differential equations, they are the same for scattering bound orbits, only boundary condition will change. So because of this simple fact, like there is a chance that having control over this function, like in this way, will give a nice analytic continuation, like in terms of this boundary conditions for your radial dynamics. So this is what they found. So essentially, when you do scattering, you go from infinity to a turning point. So that's the minimum distance. And when you do bound, you have two turning points at elliptic orbits. But the interesting part is that the two roots of the elliptic fund are related to the same root in the scattering thing. This is the big finding of this paper. And essentially, that's the only way the only way you can find this analytic continuation. So now I want to revisit back this analytic continuation and new variables. And essentially, you can do the same with these branch cut prescriptions, like for the rapidity. So you can just look at the continuation of the minimum distance here and the radial integrant in terms of the rapidity with two branch cuts. And essentially, when you integrate, both of them will appear, essentially, for the connection between the bound case and the scattering case. So there is a kind of average of the two. So it's very different from what we found for the wave function. So now I'll try to make connection later, like. And this picture generalized to align spin particles, okay? Very naturally, they stay on the plane. So you basically have another charge, okay? But you can just still have a scalar quantity, like, and talk about the dynamics on the plane. I just want to briefly talk about what happens if you LNA are on generic direction. So in this case, you have precession. You are not on a plane. So just like radiation, you are kicked out on a plane. So you need new variables because otherwise you cannot describe the system. So what we look is some generalization of the radial action. So the radial action arises from this amplitude action relation. What happens is that you can also, instead of doing that Fourier transform and get to the composition in what will be spherical harmonics, I would say, you can do in spheroidal harmonics, and that will give you like some terms that gives you the component of the polar motion, essentially, so some dynamics of the plane. And this was found by Carter. The connection with amplitude hasn't been explained yet, but essentially this is a subtle point of the spheroidal harmonics in the decomposition of the amplitude. Whereas this one is the standard part I was showing you also later. The interesting part that we found an anti-continuation that for the probe limit at all order in the coupling, which for both the radial and the polar action. And so that means that also for the probe limit for the generic orbits, this works. And there is the simplest misaligned spin configuration still works. And the probe limit is very important. Most of the stuff that has been done also in the cell force and in the EOP approach, like relies the probe limit as a kind of resummation for resummation consideration. This is very important. So I believe there is a good chance that this can be extended further in various directions. Okay.
What directions? In what directions?
Well, I just mean various directions, like in a sense like that the probe limit, people consider, for example, osculating geodesics, where you modify your geodesic to the next order, like for example, in the cell force, and then there's still a modification of the geodesic thing. So you start with geodesic, you bend it a bit more by modifying the orbital parameters. So controlling the geodesic case is always a good stepping stone, especially if you look at stream mass ratio spirals, for example. Yeah.
I mean, you say probe limit. Are you allowing for spin on the probe? I assume you're not.
No, no, not here. So you can think about including some spins. So Wojtek has this nice paper where he used the Rudiger constant. Where is he? Yeah, this nice paper on the Rudiger constant to extend this and at the linear spin order. And there is some kind of separability. So it's probably gonna work in the same direction, more or less, but I don't know yet. Yeah.
What is the N?
Yeah, so these these are some parameters which are the incoming direction of your geodesic. So to label the geodesic, you need to also to know like the initial p theta direction, and this is the number of turning points like in the polar motion. So yeah, thanks for the question. Yeah, and this LQ is generalization of the Carter constant. Well, generalization, sorry, it's related to the Carter constant. It's a square root L square plus Q, I think.
So can I have a naive question? What is happening here functionally, right? So you have the functional form of IR for unbound orbits.
Yeah.
Right.
Yeah.
Then you get the functional form for bound orbits on the left.
Yeah.
And in all of this, you substitute. Well, smaller than zero. That's how you label it here. But
Yeah.
Okay.
Yeah.
And that just
It's
works.
integrated this one. Otherwise, at the level of the orbital elements, you do some trick like those essentially. And then you look at the roots of the Kerr potential. You look at the quartic potential of Kerr, and then you look at the roots and continuation. And that will also tell you that this works. Okay. So this was enough for the conservative part. So I'm just gonna go to the new stuff now. How much time do we have? Oh, thanks. So we consider the recursion. You can just look at Swinger Dyson equation by adding a graviton. So you just consider the dressing of the Swinger Dyson, you do LZ reduction, and you find a similar recursion of this type. And this can also be solved. And this is, for example, has been shown in some the recent one loop waveform papers. And it's very similar, essentially related. Can we find a solution? Over very quick. Essentially, you can find some a positive energy. There is some evidence that this kind of iconal form does work, where you have some queen state of gravitas. But the important part is that the 5-point amplitude plays a key role here, and that's what this was the one that I was talking about was the radial action of some Hamiltonian big conservative part, and now you have a new object. So you need two objects now to describe dynamics when you have radiation. And so basically the key part is what is these objects, how do we do an anti-continuation? And this is also a dressing version of the true MPI kernel, this true massive particle histogram I was talking before. So all observables are defined for some are related to this kind of representation, and the open probe is kind of standard anti-continuation of the waveform. I'm gonna have to speed up a bit. This is the formula for the waveform in terms of the kernel, which is just the 5.3 amplitude for us now. We only talk about 3 level in PM. And that's essentially a Fourier transform of this. And the interesting part now is essentially that there are two contributions to the waveform. I was talking about positive energy before. It's very subtle to consider the zero energy. So these are called static effects, and they're related to the BMS frame. And I'm not going to be discussing much today because the analytic continuation is a bit more subtle, but we consider only dynamical bits, which is also relevant for most part of the fluxes, and we'll see how that happens. So this is a result we got with Stefano here and Pavel, and was also obtained before by the Gustavs. Is reproducing the Kovacs born for, sorry, what did I say? Sorry. Sorry. If you give me a better name, I'll do it.
It is my name.
Yeah, by Mogul Jakobsen. And the interesting part here is that we have a very compact form, which we can handle in position space in time domain. In time domain, you have only this type of square root type of structures, whereas in frequency domain, you have a lot of Bessel functions, which are more complicated discontinuities in the complex plane. So these are more easier to handle, also for the analytic continuation. And that's a closed form result for this leading order waveform. So what we do, we now have the resummation of the kernel, right? So I said that the poles are going to come from the expansion. So if you look at the kernels in the exponent, you just want the analytic continuation of the kernel in the exponent. So you don't need the residue. So that this is the kind of analytic continuation that we propose. It's analytic continuation with a single Breit-Scarp prescription, just like the one for Schwarzschild, for the wave function of Schwarzschild. How can we verify this? So we use the post-Newtonian expansion. In the post-Newtonian expansion, the center of mass frame, in time domain, you need to rescale the U. So this is because the frequency has to scale like the infinity, and essentially there is you have to reproduce restore the power source C. So to do that correctly, basically this U need to be expressed. These are what I will discuss here will come from another direction later, but you have to rescale this factor to do the PM expansion. You only find one PM and not 0.5 because of a particular property of three-level waveform. And the interesting part is these multiples can be obtained independently by quasi-Keplerian parameterization that was found by, for example, Damour and Derwell up to 1 PN. So there is an independent calculation, completely independent calculation to do, to check these things, and also to do it for elliptic. So you just do it. And that's what essentially we do. This is the kind of the equation of motion for the relative trajectory. So you consider two bodies, okay? You go into the center of mass frame. So you see 0 here, so you are in the center of mass frame. And you parameterize this in terms of something that looks like Keplerian, but actually is modified in PN by some 1/c effects. So here you will have like your 3 eccentricity radial time and phi. You will have some eccentric anomaly, hyperbolic and elliptic. And the interesting part is that they found an analytic continuation up to 1 PN. So this is, in a sense, is a gauge-dependent analytic continuation for some of the orbital elements, but it will become something gauge-independent later. And when they enter into the multiples, which is unobservable. So this is only analytically continuing this binding energy that there is this bound, okay? So what you do for the multiples, I was talking about before the multiples, these multiples tend to be computed separately, okay? This is a PM calculation. I'm expanding. I will copy the multiples just in the way that this is guided, but in time domain. What I'm solving here is the Kepler equation. The key part of making a connection with post-Newtonian and PM is solving the Kepler equation, which gives the link between time and eccentric anomaly. All the PM papers are functions of the eccentric anomaly in their results. And you want to convert back to time because time is what appears in the waveform in PM. So to convert back to time, you have to solve the Kepler equation. So you solve as an asymptotic expansion in large angular momentum. And this is how it works. So basically, when you solve this was a transcendental equation before. There is a hyperbolic sign of V and V, so it's transcendental. It cannot be solved analytically unless you use infinite sums of Bessel functions. So when you solve it in asymptotic expansion in J, you find something analytic. And this, you recover this factor I was rescaling before. This is essentially the J rescaled mean motion for people who know that the meaning, but it doesn't matter the meaning. Like, it's just the factor that appears together with T when you do this J expansion to solve the Kepler equation. So this is the way that essentially you make contact with something like a time, which, yeah, which appears like in the PN expression. So this is one example. So we do parameterization in terms of time. You compute this is the Newtonian, just for an example, multiple, and you recall, and it matches the PM 3-level expansion. Okay. And so what you can do with it up to 1 PN, you can check. Some people have written down expression, but they never check the analytic continuation. Up to 1 PN, independently of PM expansion, there is an analytic continuation. So this also works in one loop. So also one loop up to 1 PN, this will work because there is no tail effect. So the map is independently verified in PN. And also the probe limit in that specific example I was talking about before. So using the B2B map, I was thinking I'm dropping static pieces. I can consider them separately, in particular the linear memory. But using this map for the waveform, you can expand now this guy. You don't have an input parameter, in bound. So you have an angular momentum. So everything that was an input parameter becomes a function angular momentum as it should. So you do the expansion in PN, and these are the kind of waveforms that we get. This very simple plot imaginary, and real part away from the scattering one and the bound one in the COM frame for the dynamical part, which just can be uniquely identified. So it's the non-static, non-time independent part. Okay, so this
maybe you already said it. The 0.5 PN is not there, or you're not?
It's not there. It drops out. It's also written in your paper. There was a PN and PA is infinity square.
Okay, that's a low blow, Riccardo.
No. No, it drops.
For the unbound motion, there is a order V to the 1, correct?
Yeah, there is order V to the 1. Yeah.
But this is the bound one, and you're reminding me that it's not there for the bound.
I think we don't. It's just that there is a symmetry thing that for the 3-level wave, we don't consider one loop here.
No, 1 loop, 3 levels. Sorry.
Yeah.
Okay.
If I remember correctly, I think
You're saying it's not there, not that you're not looking at it.
Yeah, I think.
Okay, no, it
Yeah,
could
we
be.
should discuss separately. Yeah.
How does it cancel?
Eh?
How does it cancel? How does it vanish with an analytic?
I think I have to finish the talk, but we can discuss later. But yeah,
Discussion later.
Yeah, discussion session.
there's a
material.
discussion
Yeah.
session, right?
You can post a question in the discussion.
So
I will.
how can we get the corresponding? So if you have that waveform, that PS as an integrand of the fluxes, so you can just plug it in the fluxes. And okay, I'm gonna go over this quickly. Essentially, you can hook up some completeness relation for scattering and bound states that give you the composition, the Green function. Let's keep this part, yeah. And what it's gonna do for you is that it's gonna give you this expression for scattering, right? So this is a standard expression for computing energy radiated in terms of the waveform, where the integral is from 0 to infinity for the scattering case. But for the bound, if you've seen the papers on the fluxes, like there is an integral from 0 to t, is a bound orbit, and this is because of the discreteness of the frequency. So if you fully transform something discrete, you find a finite size integral. And okay, so now you have an analytic continuation of the integral. That is the one I was discussing before for dynamical contribution, the static dropouts in the integral in the derivative. So what you can do is essentially change variable and follow the reasoning that was discussed, like in a paper, essentially by Braffel and collaborators, and also by Bonanno and collaborators, like, and essentially using this prescription analytic continuation of the rapidity, it gives you these expressions. So this one was also found by Carlo, and this one we check at 3 p.m. in the short version. And so one interesting thing is that you have to be careful about branch cut prescription being consistent. So if you have square root of y square, square root of y minus 1, you have to be consistent in the analytic continuation of both square roots when you do this. And here it is. So that there's a table of kind of the analytic continuations for scattering and bound. So we claim this is 3-level, essentially, 3-level waveform, analytic continue to the bound one or 1 PN. And this is 3 p.m. Okay, so some of these has been verified elsewhere with other things. We verified this at 3 p.m. But some of these have not been verified with tidal effects, some pieces, so some are still conjectural. We need to study tail effects. So I'm gonna conclude here. Yeah, so basically, we derive like analytic continuation of this waveform inspired by both post-Newtonian and essentially the probe limit results. And this gives a consistent result with the Murder prescription, which was used before. And I think what's something very interesting maybe for discussion is the one with waveform, and the tail effects are very important. And the amplitude action relation for, yeah, also this one for generic spin orientation, which is still not understood. I think precession is still not understood enough in our context. So it's something. Thank you.